Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. You know, the Griffin Museum of Science and Industry in Chicago is a science museum that I kind of grew up with growing up in Southwest Michigan. And they have a Foucault pendulum. Let's go ahead and use the Foucault pendulum at the Griffin Museum of Science and Industry to calculate the gravitational attraction of Earth and the sidereal day, or the rotation of Earth. We're going to simply use the swing of 8.875 seconds, the length of the cable at 19.656 meters, and the latitude of the Chicago Museum at 41.79 degrees north. Now I've gone ahead and put that information down here. Like I said, the latitude, 41.79 degrees north. Local gravity in Chicago is 9.803 meters per second squared. And a sidereal day is 23.934 hours. Measured pendulum time is 8.875 seconds. Now when we try and figure out what the period of a pendulum is, it's 2 pi times the square root of the length of the pendulum over local gravity. Now this is for an idealized pendulum, one that has no mass to the cable, has no other forces acting on it. It's just strictly the pendulum. When you're dealing with a physical pendulum, as Clive pointed out the other day, you actually have to take into account the angle of the swing. Now, the angle of the swing, theta, in Chicago is 3 degrees. And the formula to find the corrected period is that you take the original measured period and you multiply that by 1 plus the swing angle squared divided by 16. Now the swing angle is listed in radians, not degrees, so we have to convert the degrees to radians. Well, 3 degrees is pi over 60 radians, and if we square that, we get pi squared over 3600, and then we divide that whole thing by 16. We take that value, we add it to 1, and then we multiply the measured period, which is 8.875 seconds, by that whole mess. So let's go ahead and do that real quick. What we find out is that the corrected period for use here is going to be 8.897 seconds. You see, it's a little bit different. It's a very small correction, as you can see, but it's important, especially when you're doing precision work. So let's go back to our pendulum equation here. Let's go ahead and solve for what gravity is going to be. Let's see how to do that. Well, first thing that you would do is you would take the period and divide out 2 pi to get rid of this here. That'll equal L over G, the square root of that. Then what you do is you take T over 2 pi and you square it. That will equal L over G. Then finally we can multiply both sides by G and divide both sides by the square of T over 2 pi. And we end up with this equation. And that's how we solve for G. Now we do something in math called plug and chug. All we have to do is put these numbers in. So G will be the length of the pendulum, which we know to be 19.656 meters. We know the period of the pendulum, which is 8.897, which is the corrected period right here, over 2 pi, and then we're going to square that. And we're just going to divide it out. What do we get? We get 9.8032 meters per second. So what is the reported gravity in Chicago? Well, it's 9.803. And as you can see, that's what we ended up getting down here. So the first thing that we did was we took the actual data from the Chicago Foucault pendulum and used it to calculate gravity, using nothing more than the length of the cable and the time of the swing. Now let's use that same data to calculate the rotational speed of the Earth. Now the time that it takes a Foucault pendulum to precess 360 degrees can be calculated very easy. So time of precession will equal the sidereal day divided by the sine of the latitude. Now in this case, we actually know the latitude of Chicago. That's 41.79 degrees north. And we know the precession of the pendulum. So we'll put in TP here equals 35.71 hours. And we'll use these values to calculate what the rotational period of the Earth is. So again, we're going to move this around a little bit. We want to find the sidereal day, so we take the time of precession and we multiply it by the sine of the latitude will equal a sidereal day. So what is the time of precession? 35.71 hours. And then we need the sine of 41.79. Once again, let's plug and chug. Okay, so I went ahead and put the math in. So we've got 35.71, which is the number of hours for one complete precession of the Foucault Pendulum in Chicago. We look at the sine of 41.79. It's 0.6664 Hale-Sagan. And if we multiply those out, we get a sidereal day equals 23.7972 hours. Now, a real sidereal day, the actual accepted standard, is 23.934 hours. And that's the famous 23 hours, 56 minutes, and 4 seconds that everybody talks about. So you see we're a little bit off right here. Now that value is off by about 0.1368 hours. And what does that equal in real time? That's about 8.2 minutes. Honestly, 8 minutes and 12 seconds is well within the expected margin of error for a Foucault pendulum that is a demonstration model for public review in a public hall with varying humidities and air currents of people walking around, etc. We're really not doing too bad if we got within 8.2 minutes of the correct rotation of the Earth simply by looking at a ball swing on a chain. Now, the last thing that I want to do is I want to see if, given the sidereal day length and the amount of swing of the pendulum in Chicago, can we calculate the latitude of Chicago? Well, as it turns out, we can. So if you want to look at the time of precession, that's going to equal the sidereal day times the sine of the latitude. Now we can rearrange this a little bit and say that the sine of the latitude will equal the sidereal day over the precession time in Chicago. Well, that's pretty easy. We have both of these numbers. So the sidereal day is 23.934, and the precession in Chicago is 35.71. That value right there equals the sine of the latitude. Now we can actually do this a little bit backwards and find the actual latitude using a function called the arcsine. And on your calculator, it's a secondary function under sine that says sine and then -1. Now when we do that function, what we find is that we get a latitude for Chicago of 42.085 degrees north. And as you know, the actual latitude of Chicago is 41.79. So if you subtract 41.79 from what we get, we find that we are about 0.295 degrees off. And that works out to about 32.745 kilometers. Our measurement puts us in the North Chicago suburbs. It's off, but it's only off by about 32 kilometers. Well, that's about 20 miles. So once again, we calculated gravity, we calculated the duration of a sidereal day, and we calculated the location of Chicago. Didn't have to look at the stars, didn't have to use any satellites, didn't have to use a sextant. All we had to do was get some careful measurements of a ball swinging on a chain, and we got better measurements than any flat earther could ever hope to get. So, this is Bob the Science Guy. Thank you very much for stopping by. In my next video, we're going to actually look and see how the Foucault pendulum demonstrates that the Earth is indeed a sphere and not flat. So, until then, take care, guys.